So welcome you all once more for this festival, Sundar Fest, right? So our first speaker is Professor K.B. Sinha from JNCSR. So and his title is On the Koplanco Trace Formula and Beyond.
Morning. It is a great pleasure to be here. In fact, when Vijay wrote to me saying that such a thing is being planned, I think I must have been he wrote back saying that the fastest reply of acceptance. I had obviously no doubt that I would be present here on whichever day they plan to do it. So I'm once again very glad to be here. Sundar and I, our trajectories have intertwined in various times and places. Maybe we'll talk about it tomorrow afternoon. Okay, so today what I will talk about is something I've been working on with a student of mine, Arup Chattopadhyay, for the last year or so. And so let me begin. Now I am technologically somewhat challenged. All that fancy thing that you see is due to Arup, not due to me. So let me give the next slide, which is mostly to motivate. This is mine, yes, indeed. So this is a simple matter of matrices. So let A and B be two complex n by n symmetric matrices, and you define a sort of a map from the interval 0, 1 to a family of symmetric matrices constructed as A plus SB. So the map, so look at the eigenvalues of the symmetric matrix and its dependence on the parameter S. Then this is a piecewise differentiable family of eigenvalues of AS. This is a well-known result. For example, you can look up Kato's book. Now, if you look at the eigenvalue equation and differentiate it and do a little bit of manipulation, you will get that equation that you, yeah. I should have said self-adjoint, yes. Hermitian I should have said, yeah. Yes. So the conclusion is at first looks a little surprising to me. When I first looked at it, that was maybe 10 years back, when I saw this result for the first time, I was a little surprised, but that trace of the perturbation B, let's look at B as a perturbation of A, and look at the spectral family of ES is the spectral family of the family of self-adjoint operator matrices AS. If you look at just the trace, this is obviously not absolutely continuous with respect to the Lebesgue measure. But if you integrate over S, over the whole parameter space 0 to 1, then that becomes, yeah.
The first equation,
yes, sorry, yes. Phi Js is missing, yes. So you write down the eigenvalue equation and differentiate. So this the averaged or integrated density is kind of is absolutely continuous with respect to Lebesgue measure. And what is also surprising but true is that this observation remains true in infinite dimension as well, and that is the content of what is known as Crane's theorem, which goes under the last line. That is, if you look at function of perturbed operator A plus B, phi of A plus B, and subtract from it phi of A, take the trace thereof, the integral that is given by the first derivative of the function phi integrated with respect to that density function called Crane's shift function. Now this has been source of a lot of literature, and this formula, and under what kind of conditions you can prove such a thing. And many proofs have appeared, starting with Crane's original proof, which goes back to 58 or 59, which uses function theory, and then subsequently other people proved differently. In fact, okay, so this is now starts the little technically better presented, yeah. So now let H and H0 be to possibly unbounded. So this theorem is true for unbounded self-adjoint operators as well, such that the difference, that is the perturbation, is trace class, that is traceable. Then Crane proved this theorem. Oh, sorry again, this A to B would not appear, okay, A B could be infinite, that A could be minus infinity, B could be plus infinity. There exists an L1 function, that is a Crane's shift function Z, such that the difference, trace of the difference is given by the integral with respect to the that function and the first derivative of the function phi. Now you can think of it as a kind of a mean value theorem under the trace. So you have phi of H0 and phi of H0 plus V. Their difference is given on the average. On the left hand side, average is given by trace, right hand side average is given by the integral with respect to this L1 function xi. Now Voiculescu in 1985 approached the formula trying to establish the, as I said, many people proved this formula in many ways, and Voiculescu's way was the following, that he first tried to cut it down to finite dimension. So you try to prove the formula for finite dimension, and then by a limiting process you go to the final formula. Now the cutting down is specific to the operators involved. So you use some kind of adaptation of Weil von Neumann theorem, where here in this case P is polynomial and H0 and H0n are the truncation of the given operators to that finite dimensional subspace. Then the philosophy is that you construct the spectral shift function for the finite dimension and then take a limit appropriately to get the infinite dimensional case. Now I had a hand in it to extend this to a Voiculescu type of philosophy to unbounded case long time back. Now what happened? Oh, okay. So one can think of this as a mean value theorem under trace, and then a natural question arises if one can have a mean value theorem under trace up to the next order. So you want to extend it to the next order, and Koplanco indeed asked such a question and provided a formula. Now his theorem, his proof appeared in one of the Russian journals, and it is wrong, which was detected some decades after. In this case the difference phi of h minus phi of h naught is no longer trace class, because V is Hilbert-Schmidt, B2 means Hilbert-Schmidt class. So you have to subtract the first derivative. So by capital D I mean the Fresher derivative of the function phi at h naught acting on V. Well, and then find a trace formula for the above difference. So it is the next order in a sense. Then Koplanco formula asserts that exists an unique L1 function such that you have the second order formula. So phi of h minus phi of h naught minus the Fresher derivative acting on V. This trace thereof is given by the second derivative of the function phi averaged over a certain L1 function. But he proved it for phi rational functions with poles of the real axis, for that class of function. This function is called Koplanco's function. Now this was proven long time back, I think in the 80s Koplanco's formula was proven, but more recently 2007 Gestesi and Simon etc. et al. Took it up and gave an alternative proof for the bounded case, that is when h and h naught are bounded. Now we try to prove the formula by a method of finite dimensional approximation that we used for Crane's formula as well, and extend the same for the unbounded case where h naught is unbounded, but the difference remains in Hilbert-Schmidt class, and the functions are much larger class of functions for which this formula we managed to prove. Now of course this is an unending question. You can go on asking how about the second order etc. and third order and so on. I will have something to say in the end on that. Now I should also mention that maybe it is there in the next slide. No, Dykema and Skripka, I think one of his students, also attacked this problem, but not the way we did, not by finite dimensional approximation method, but directly using some ideas from free probability, which of course you expect from Dykema, but uses the inverse Cauchy transform techniques to prove these results. But the real challenge is to prove, you see, to get a measure is relatively easy. That is, instead of eta lambda d lambda, but some measure mu d lambda is not that difficult. But to show that that measure is absolutely continuous is the really hard part of the whole analysis. And they managed to prove existence of measure for a different class of function phi, and but in some cases they can show that the measure is absolutely continuous, some cases they cannot. So let me quickly give a little bit of an idea of how we go about proving it. Okay, for bounded case, it suffices to look at polynomials. And since we are going to take we are going to subtract the first order derivative, so you have to look at polynomials of degree greater than or equal to 2. So given that, it is easy to compute these I'm pressing it the wrong way. Okay, so you compute the fresh derivative, and that is exactly this expression. Now, as I had said in my introduction, you introduce this map from the interval 0, 1 to the family of self-adjoint operators given by H sub s, and you try to find the derivative with respect to the parameter, and that has very similar expression to the fresh derivative, because this is actually the Gateau derivative in the direction of v, whereas this is the fresh derivative. So it is not surprising that they look similar. There exists then the statement is that there exists a non-negative L1 function eta such that this formula holds. Now, so let me go back to the Crane's formula. Crane's formula, which is maybe called the 0th order formula, this function xi or z has an interpretation coming from physics. That is where H naught is to be interpreted as Hamiltonian of a system, H is a perturbation thereof, and then z or xi function is interpreted as what is known as phase shift, or sort of averaged out phase shift function, which in scattering theory physicists do study. Now, in this case, Koplanco case, this is the Koplanco formula in this context. So let us look at the polynomial expression. This eta is a non-negative, unique non-negative L1 function. The non-negativity is a little bit of a surprise, and I do not think any interpretation exists, that at least I do not know of any interpretation of this function eta, unlike the Crane's function. So this is a statement of the theorem for bounded operator H naught. Okay, this part of the statement is finite dimension. We do not need to do everything in infinite dimension. So finite dimension, you have even a formula for eta, expression for eta, precisely so. Again, you notice there is an averaging with respect to trace as well as the integral in ds. Just as Crane's case, to remind you again, wrong arrow here. So try to imagine this formula for the Crane's function. So here is the integral ds, here is the trace, b has become v there, es is the spectral family of hs there, and this averaging is giving you the xi function. And in the Koplanco case, it is firstly here is the perturbation v in place of b, but you look at the difference of the spectral family, and then you average or integrate over the parameter s, and this gives the Koplanco function. So it is kind of instructive that, you know, as you go order by order, then it changes the expression in a very systematic way, and the L1 norm of eta is precisely up to a factor, the Hilbert-Schmidt norm square of the perturbation. Well, the proof I think I should skip. Raja, what is the, how am I doing? How much time do I have? Okay, so roughly speaking, I mean, you just look at the difference of the powers and you do a little bit of manipulation, and So you prove the, okay, that's elementary, and similarly the Gato derivative is also elementary. Now you use the trace, cyclicity of the trace, and you have this formula that you establish that this Koplanco difference, let's call that Koplanco difference, can be cast in this form, that this Gato derivative, integral of the Gato derivative over the path 0, 1 minus the fresh derivative, which is the value of the Gato derivative at 0. And then you do a little bit of integration by parts. So at this point you do integration by parts, and remember we are in finite dimension for this part of the calculation. So the boundary term vanishes because you have a difference, and you get the formula that you are looking for. So this just explains that the boundary terms vanishes, and we get the formula that you are looking for, where the Koplanco function has the form that I had written earlier. Uniqueness of eta follows from the uniqueness of a probability density supported in a finite dimensional finite interval with a given sequence of moments. Because you take all the polynomials and that will give you the moment equation, and all the moments must be the same, and that gives you the given sequence of moments and gives you the uniqueness. Now positivity, we use the idea going back quite some decades due to Birman Solomiak, the Russian group. So what do? We approximate the spectral family by a smoothed out spectral family, which is continuous from the right, and which approximates the spectral family which is continuous from the right. And then you look at the difference of this approximate spectral family for H naught and H naught plus the perturbation, and you get this simple formula. Okay. So here is the difference of the function divided by this argument difference, and you have this measure. Now what kind of an object is this? This is a measure in the square AB to cross AB, and V is Hilbert-Schmidt. Okay. So we are, though we are in, I mean, for this you think of it, you are in infinite dimension. So V is Hilbert-Schmidt. So think of this as a measure on the plane, and you can prove that this is indeed a bona fide measure in the plane with finite variation and with total variation less than equal to well, this is wrong. It should be the Hilbert-Schmidt norm of V. That should be the total variation of this measure on the square. So phi so this is the measure, we have just given it a name, and this therefore I hit it with V on the left hand side and take a trace. Then I get this quadratic form of so this gives a numerical measure of finite variation, and then this is non-negative because this is non-negative, and this is negative because it is a decreasing function. So the difference quotient is negative, and here there is a minus sign, thereby proving this positivity of this expression for approximate spectral families. Well, this is since, not science. So therefore, since these converge strongly to the spectral families respectively, as epsilon goes to 0, epsilon is the approximation parameter, and the spectral family is right continuous in our definition, it follows that the object of our interest is non-negative. Therefore, eta is non-negative because eta is an integral of those expressions, that this, it is an integral over S of this expression, and the total L1 integral of eta, L1 norm of eta is, since eta is non-negative, can be easily evaluated by taking square of the polynomial as lambda square, and you evaluate it, it gives you exactly what has been mentioned before. So total L1 norm is related to the Hilbert-Schmidt norm of. Now the approximation part, how do we come from the infinite dimension to finite dimension, and that is an adaptation of Weil von Neumann. So the statement is, this I won't prove. So A is a given self-adjoint operator in an this is infinite dimensional Hilbert space now, let Fj be a set of normalized vectors in H and epsilon is a given positive number. This is a finite family J from 1 to L. Then for A is fixed, Fj's are fixed and epsilon is fixed. For these three fixed things, there exists a finite rank projection P such that 1 minus P Fj norm less than epsilon, and furthermore that is P perp A P is Hilbert-Schmidt, and Hilbert-Schmidt norm can be made less than this epsilon. I mean, that is how the P has been chosen. And furthermore, the exponential instead of, I think this is about to die, is also can be estimated similarly uniformly in T for T in a compact. So, this I will not prove, essentially adapting Weil von Neumann's proof. Von Neumann's proof of Weil's theorem. So now we go back to our problem. H and H naught be two given self-adjoint operators such that the difference is Hilbert-Schmidt in infinite dimension. That given, so what we do is essentially look at the canonical form of V and then chop it off at L suitably such that L is chosen by this. Given epsilon, L is chosen so that the truncation is within epsilon distance in the Hilbert-Schmidt norm. So, we reformulate by that there is a sequence of Pn such that we have these things converging to 0, but one should be cautious that it does not mean that Pn converges to identity as strongly to identity. Okay. Pn is a sequence which looks like going to identity, but not on arbitrary things. It is manufactured for the given operator H naught and for the given for the given operator H naught and V. Okay. Okay, now this I will skip. So what you do is that, okay, so this is just the statement of the final theorem. So let me give just an idea. So first is that the Weil von Neumann type of truncation which I described gives me a Pn such that this trace can be computed by computing the truncated trace and taking limit thereafter. For truncated trace is a finite dimensional problem, so I know there exists a sequence eta n of non-negative L1 functions such that for this the formula holds. And in fact, we have an explicit expression as I had written earlier. But these are all finite dimensional truncation of the original operator. So what we are left with is to show that eta n forms an L1 Cauchy sequence. But you can to prove it directly is almost impossible. So what you prove is looking at it in the dual. So you take an arbitrary function f in a bounded function over the interval, this is the bounded case, and look at these integrals and want to show this goes to 0 uniformly in the L infinity norm of f. Okay. That is what you do. It is a bit of a calculation, but it works. Now when you want to go to the unbounded operator, if H and H naught are not bounded, that means your interval becomes infinite, then you will have to switch over to the unitary group instead of polynomials of the operators involved, and exactly similar kind of thing can be done for exponentials of unbounded operators H naught and H. The philosophy is identical, and you have to just carry through the computations and you indeed get a similar kind of proof, except only thing you have to pay attention is that when doing this proof f is L infinity, and what we do is that the integration by parts that we did has to be undone. That means you have to look at the integral of f. When f is over a bounded interval, it is a bounded function over a bounded interval, the integral of f is also bounded. But when it is a integral of a bounded function over an infinite interval, the integral ceases to be bounded. So that creates a little bit of a problem, but can be handled. So the theorem is, final theorem is H and H naught are two self-adjoint operator in infinite dimension. notice they are not necessarily bounded. I do not say they are bounded, such that the difference is Hilbert-Schmidt, and let us say phi is in Schwarz class, then this difference, Koplanco difference, let us call that, is is trace class. Furthermore, the trace is given by the Koplanco formula, where eta is a unique non-negative L1 function with that L1 value. Now, you do not anymore have an expression for eta, all you know there exists a unique L1 function. And furthermore, as a remark, you can say that this formula can be extended. You do not really need a Schwarz class function. Any function which can be given this form, where nu is a complex measure, and it can have a linear term additionally given, so that it is kind of a transform of a certain any complex measure. Then for such class of phi also you have such a formula. Only problem is the left hand side may not be interpretable as an operator. So that is a word of caution, because this integral, if you think for a minute, is essentially effectively quadratic. If it is quadratic in lambda, then the operators will be quadratic, h square and h naught square here. So even if V is bounded, it is Hilbert-Schmidt in fact, so the domains of h naught and h naught and h will be the same, but domain of h naught square and h square can be a little complicated. So domain of phi of h and phi of h naught may not have enough good intersection. So as whenever the left hand side is defined as an operator, then this formula holds. That should be the statement for the unbounded case. Now, okay, so I am doing pretty well. Now back to my technology. This is the part beyond. So what one can do beyond what I have said so far? One can do the following, go to the next order as I had said. No names are associated with this formula. So this is for the bounded case. So again I am sorry that I am changing notations. This is for the bounded case. A is a bounded self-adjoint operator in infinite dimensional Hilbert space. V is now notice the Schatten class is changing with each order. The Schatten class changes by 1. This is B3, the third Schatten class, and self-adjoint. Then there exists a bounded measurable function, and the class of the function is also changing, such that you have I think this is dead. You have this formula where you have the, notice I have subtracted the second derivative, second fresh derivative as a quadratic bilinear form on V. Okay, so that's the second order derivative. Then this is a polynomial function. This is the third derivative here, and you have this function kappa. And the integral of kappa is not anymore non-negative. I mean, we can't. There is no definite sign to it, unlike the Koplanco case. And this will be up to a factor trace of the V cube. The step here is are the same as Koplanco formula, but much more complicated. The hardest part is to derive the formula in finite dimension. Such an object in finite dimension, you can compute everything, but how to put it in the form that shows in the right hand side is a bit of a challenge. And we have only very recently been able to find some kind of an expression which is given there. Now I have to explain what these V1 E tau, well, E tau and Hs are the same, except that notice here there is a double integral now with respect to the parameter. It is an iterated integral in the lower part of the simplex, integral 0 to s and integral ds 0 to 1. So you are in the square, you are integrating in the lower part of the square below the diagonal. So what is V1 and V2? Okay, so with respect to the Hilbert-Schmidt inner product in the space of matrices MNC, the canonical decomposition of V you take as V1 direct sum V2, or V1 tau direct sum V2 tau with respect to the parameter tau. So when tau is 0, we call it V1 V2. So V1 is coming from the commutant of A. A is the given operator we start with, and V is the perturbation. And V2 is in the range of this commutator. that is V2 can be written as a commutator y for some y. And similarly V1 tau is just the commutant of a tau, and V2 tau can be written as a commutator of a tau with some y. So going back to the formula, so it is those V1, V2 etc. they appear in this expression. So there are so there is one which is that just the spectral family appears, and one which is the integral of the spectral family appears. So that is we have not yet completed this program for this part, that is we have not yet achieved the limiting process, that is still to be done. Now next thing that one can do, and this is a bigger challenge, that is more than one variable. So here von Neumann-Weil theorem, which we had used to truncate the problem to finite dimension, we look at the Berg's modification of von Neumann-Weil, and we modify it as follows. So this is a theorem we have been able to prove for n tuples, commuting n tuples. So A1 into An, be n commuting self-adjoint operators in infinite dimensional Hilbert space. Then there exists, now in this case there exists a sequence of Pn of finite rank projections increasing to identity. So this is really the strong converging sequence of projections now, such that the commutator of each of them with this projection in the P norm goes to 0 as n goes to infinity for each j, but the problem is the P, the certain class, certain norm has to be greater than the number n. So for example, if I had 2, which is the next thing that one would like to work with, it becomes greater than 2, it just misses 2, P greater than 2, and that does give rise to certain difficulties. Now and such things, this kind of expression 1 minus Pn Ag Pn, that is Pn perp A Pn, occurs frequently in all the calculations that have preceded, that in the reduction of the problem to finite dimension, and here also this and this are the same, essentially same. Therefore, for example, in finite dimension, well, I mean, we can prove this in infinite dimension. So take two functions phi j, let us say in Schwarz class, over the plane R2, and take two tuples H and H naught. So H01, H02 they commute, H1, H2 they commute, the two commuting pair of self-adjoint operators, and you would look at phi 1 of H, that is tuple, and subtract from it phi 1 of H naught tuple, and similarly take another function phi 2 of H minus phi 2 of H naught tuple. This product is in B1, is Tress class. I have said somewhere Vj, this is wrong, this should be V4, it is not B2, because my n is equal to 2, so according to the previous theorem P should be greater than 2. So I have written it wrongly here, it should be B4. So in particular I can choose it to be B4, then this product, well, this is dead. So this product is going to be in B1, and so at least we are able to prove that there is a finite dimensional truncation of this problem, provided we take a product of differences, not one difference like the previous single variable theorems. So now that this is trace class, one can look at the trace of this product and try to see how the formula looks like, and here geometry is expected to play a role because you are no more in one dimension. So question is, we are not yet able to derive a formula of geometric significance, and we are looking for, we have a formula, but that formula does not have obviously any geometric feature that we can find. So this is where we are, and I will stop here, and thank you for listening, and happy birthday Sundar.
4 times, so we have a lot of time. She's asking for reference.
Okay, sorry, the references are here, yeah. Well, these are not all the references, just some selective references.
Any question?
You mentioned
Berg, B-E-R-G.
So there is was it for normal operators, right? Divide over normal operators, right?
No, his statement was slightly different. No, it is for n tuples. For n tuples of, if it is tuple, then it is a normal operator, okay, statement.
No, I thought that's what he proved. I thought he proved for normal operators.
Yeah, but it can be extended to n commuting tuples without too much effort. But his statement was different. His statement was that if you are given n tuple of commuting self-adjoints, then you can find a diagonal operator, that is, a diagonal operator such that the difference is in operator norm is compact, and the operator norm can be made arbitrarily small, less than epsilon, given epsilon. Here we are looking at the Schatten class also. We are a little bit more finer, that's all.
But the Schatten class cannot be got down to 1.
So far we are not able to bring it down below n. I mean, it has to be greater than n. Our estimates are not strong enough for some, I don't know, we are not able to improve it.
Any other question? I have one question. You have some connection with these Horn's inequalities and these things?
Which inequality?
Horn's inequalities and this.
I am not that knowledgeable about the Horn's inequality, I must admit, but I don't see any connection immediately. I would be expecting for the 2 variable, for example, I would be expecting a formula which gives me on the right hand side some kind of a Stokes expression, Stokes integral with respect to the 2 functions phi 1 and phi 2. So you will have a d phi 1 wedge d phi 2 with some function of 2 variables. That this will be now a function of 2 variables instead of a function of 1 variable. But I cannot yet cast it in the Stokes form.